Today we are solving LeetCode 1622, Fancy Sequence. Before we get into the actual problem, let's start with a short analogy. If you'd prefer to skip it, you can move to the next timestamp where we begin the problem directly. Imagine a commander training a squad of soldiers. Every soldier has a power level. Sometimes the commander orders increase everyone's power by 3, and sometimes double everyone's power. If the squad has thousands of soldiers, updating each soldier every time would take too long. So instead, the commander keeps track of 2 global modifiers that represent the total upgrades applied so far, and each soldier's real power is calculated using those modifiers. That is exactly the strategy used in this algorithm. Now moving to the actual problem, we need to design a sequence that supports 4 operations. First, append with value val, which adds a number to the end of the sequence. Second, addAll with increment inc, which increases every number in the sequence by a given value. Third, multiplyAll by m, which multiplies every number in the sequence by a given value. And fourth, getIndex idx, which returns the number stored at that index. All answers must be returned modulo 1,000,000,007. If the index does not exist, we return -1. Now, when reading the question, a few signals immediately stand out. On my website, I summarize this using pattern recognition signals. First, we see operations that modify every element in the sequence at once. That is usually a sign that we should avoid updating each element individually. Second, we have append operations combined with bulk transformations and queries. This pattern often leads to maintaining lazy global transformations. Third, the updates are linear transformations. Every update either adds a constant or multiplies by a constant, which means the overall transformation can be represented with a simple formula. Fourth, the number of operations can be up to 100,000, which means any solution that repeatedly scans the entire array would be too slow. And finally, the problem involves modulo arithmetic, which hints that modular inverse operations may be required. All of these signals strongly point toward using a lazy affine transformation technique. Now let's understand the underlying concept. Instead of modifying every element, we maintain 2 global variables, a multiplier and an addition value. At any moment, the real value of an element follows this rule. The actual value equals the raw value multiplied by the multiplier plus the addition value. In simple words, we store the base value and the global variables represent all operations applied so far. This means we never update every element directly. Let's see how each operation works. For addAll with increment incs, every element increases by the same amount. Instead of updating the entire array, we simply increase the global addition value by that increment. For multiplyAll by m, every element is multiplied by m. If we apply this to the formula, both the multiplier and the addition must be multiplied by m. So we update the global multiplier by multiplying it with m, and we update the addition value by multiplying it with m as well. The interesting part happens during append with value val. We cannot store the value directly because the current transformation would affect it later. Instead, we reverse the formula. We want a raw value such that after applying the transformation, it becomes val. So we compute the raw value equals val minus the current addition value multiplied by the modular inverse of the multiplier. Because the modulus is a prime number, we can compute this inverse using Fermat's little theorem. This allows us to store a base value that remains correct after future operations. Now let's walk through an example. Start with an empty sequence. The multiplier is 1 and the addition value is 0. Operation 1. Append with value 2. We compute the raw value as 2 minus 0 multiplied by the inverse of 1, so the stored value becomes 2. Next operation. addAll with increment 3. Instead of modifying the array, we simply increase the addition value. Now the sequence behaves like 2 plus 3, which equals 5. So the visible sequence becomes 5. Next operation. Append with value 7. We reverse the formula again. 7 minus 3 multiplied by the inverse of 1 gives a raw value of 4. So the stored array becomes 2 and 4. But the visible values are 2 plus 3 equals 5, 4 plus 3 equals 7. So the sequence appears as 5 and 7. Next operation. MultiplyAll by 2. Now we update the global variables. The multiplier becomes 2 and the addition becomes 6. The real values now become 2 times 2 plus 6 equals 10, 4 times 2 plus 6 equals 14. So the sequence becomes 10 and 14. Notice something important. We never updated the stored values directly. Everything was handled by adjusting just 2 numbers. Now let's briefly look at the code idea. We maintain 3 components: an array storing the raw base values, a global multiplier, and a global addition value. For append, we compute the reverse value using the modular inverse and store it. For addAll, we update the addition value. For multiplyAll, we update both the multiplier and the addition. And for getIndex, we reconstruct the value using the formula: raw value multiplied by multiplier plus addition. All calculations are done modulo 1,000,000,007. Finally, let's talk about complexity. Each operation runs in constant time, except append, which requires computing a modular inverse. That takes logarithmic time, often described as big O of log p, where p is the modulus. Overall, the system easily handles up to 100,000 operations. The space complexity is big O of n because we store the base value for each appended element. And that's the complete idea behind this problem. Thanks for watching. If this helped, consider liking, commenting, subscribing, and sharing. For more problems explained like this, check out the playlist linked in the description.